Properties of petroleum reservoir rocks. Surface forces and capillary pressure. Fluid-rock interaction.
The study of fluid-rock interaction is of fundamental importance to reservoir engineering. Not only does such interaction influence fluid flow through the reservoir, it also plays a dominant role in the distribution of fluids within the reservoir's pore space and, more importantly, it dictates the maximum amount of a fluid that can be withdrawn from the reservoir. We shall start with the simplest form of such interaction, and then move up to more complex ones.
Surface and interfacial tension.
In dealing with multiphase systems, it is necessary to consider the effect of the forces at the interface when two immiscible fluids are in contact. When these two fluids are liquid and gas, the term surface tension is used to describe the forces acting on the interface. When the interface is between two liquids, the acting forces are called interfacial tension. Consider the two immiscible fluids, air, or gas, and water, or oil, as shown schematically in following figure. A molecule at the interface, however, has a force acting on it from the air, gas, molecules lying immediately above the interface and from liquid molecules lying below the interface. A molecule at the interface, however, has a force acting on it from the air, gas, molecules lying immediately above the interface and from liquid molecules lying below the interface. Resulting forces are unbalanced and give rise to surface tension. The unbalanced attraction force between the molecules creates a membrane-like surface with a measurable tension, i.e., surface tension. The following figure can be defined in terms of an immiscible fluids, oil and water, in which case the resulting unbalanced forces at the surface give rise to interfacial tension. The unbalanced attraction force between the molecules creates a membrane-like surface with a measurable tension, such as surface or interfacial tension. Therefore, the interfacial or surface tension has the dimensions of force per unit length, usually expressed as dynes, cm, and is usually denoted by the symbol. The interfacial tension or surface tension entirely fluid property and not a petroleum reservoir rock property. High interfacial tension indicates immiscible fluids and low IFT indicates miscible fluids. If a glass capillary tube is placed in a large open vessel containing water, the combination of surface tension and wettability of tube to water will cause water to rise in the tube above the water level in the container outside the tube as shown in following figure. The water will rise in the tube until the total force acting to pull the liquid upward is balanced by the weight of the column of liquid being supported in the tube. Assuming the radius of the capillary tube is r, the total upward force underscore, which holds the liquid up, is equal to the force per unit length of surface times the total length of surface. The total upward force underscore, which holds the liquid up, is equal to the force per unit length of surface times the total length of surface. The total upward force underscore, which holds the liquid up, is equal to the force per unit length of surface times the total length of surface. The upward force is counteracted by the weight of the water, which is equivalent to a downward force of mass times acceleration, or the upward force is counteracted by the weight of the water, which is equivalent to a downward force of mass times acceleration, or because the density of air is negligible in comparison with the density of water. Equating the upward force and downward force. Where
Effect of pressure and temperature on interfacial tension.
Since gas, oil, and water coexist at a variety of high pressure and high temperature conditions in petroleum reservoirs, it is important to understand the effect of these variables on IFT or ST. The variation of IFT or ST with temperature and pressure strongly influences the transport of fluids in a reservoir and therefore are fundamental to the understanding of the role of interfacial forces in oil recovery. Surface tension generally decreases with an increase in pressure and temperature. As temperature increases, the kinetic agitation of the molecules and the tendency of the molecules to fly outward increases, resulting in a decrease in ST values as shown in figure. The effect of pressure on ST is also somewhat similar to the temperature effect. The high-pressure gas phase tends to develop miscibility toward the companion liquid phase, thereby reducing ST as pressure increases.
Capillary pressure.
Capillary phenomena occur in porous media when two or more immiscible fluids are present in the pore space. A difference in the pressure across the interface due to interfacial energy between two immiscible phases results in a curvature of the interface. The rise or depression of fluids in fine bore tubes is a result of the surface tension and wetting preference and is called capillarity. Capillary pressure equals pressure of the non-wetting phase, pressure of the wetting phase. There are three types of capillary pressure. Water, oil capillary pressure. Gas, oil capillary pressure. Gas, water capillary pressure. Applying the mathematical definition of the capillary pressure as expressed by if all the three phases are continuous, then, referring to following figure, the pressure of the water phase at point 2 is equal to the pressure at point 4 minus the head of the water, or the pressure just above the interface at point 1 represents the pressure of the air and is given by the capillary pressure is 0 in a horizontal or plane interface, therefore, I appreciate your attention. Please subscribe to the channel to get all the new updates.